In the next section, I'll show you a solution to this problem. Maintain an array that you can fast access by index, but also change. That's not usually how binary search trees are presented, but I think that's the key abstraction that is actually often so useful. They have other uses, though. So let's talk about binary search trees. Before we do that, let me again check what the audience already knows. As the attentive listener may recognize, the same set of answers as we had for the heaps. So we had something like 110 earlier, 118. Okay, it seems most people got that right. Remember, number 3 was the heap. It's a subtle difference between the two. So this one, that's what we called a heap ordered tree, referred to last week. Binary search tree is this one. We'll discuss it in detail. So as I said before, think of them as some magic solution to have a dynamic sorted array. I'll explain more what I mean by that. What is it, though? So it's, again, a binary tree, which is the same beast as we started with for heaps. It's any kind of structure where we have nodes, and they have a left and a right child. And both of those can be empty. Now, I didn't go into this detail before, but maybe it's useful to have something closer to programming syntax. So if you think about a UML diagram for some class that represents such nodes, for our symbol tables, it would probably have these 4 fields. It would have a key that it stores and a value. And then it would have a pointer left and a pointer right. Remember, either of the two can be null, so then the node doesn't have that kind of child. In the following, I'll draw the null pointers like this. A little square means there's nothing, and the circle means this is a node. Good. So a binary search tree is any binary tree with the following restriction, namely that it has this search tree property, or the search tree order, which refers to the keys. Nobody can read that. All the keys in the left subtree are smaller than the key at the root, and all of those in the right subtree are bigger. Now, and that's true recursively throughout the tree, or it's true for every node and its subtree. So not just at the root, but in every point. Okay. Let me show you an example. This is a binary search tree with some keys shown in as numbers, in the nodes as numbers. In all of the following, we will never deal with the values. The values are always just carried along. I said it before. They don't change the data structure. So we don't show them in the drawings usually. And then you have a left and a right child indicated with the lines. Now, I want to point out that I drew the tree in a specific way. You can draw the tree in another way. For example, why did I choose to put node 12 so far to the left? You don't have to do that, but I think this is the one and only way to draw the tree that makes the sortedness visible. So it's drawn such that at every node, the entire left subtree is to the left of that node, and the entire right subtree is to the right. Okay, so I take the root, I draw this line down, and then left and right subtree stay in their lane. And that's true recursively. If you do that, that means you project down the keys to a certain x position. And if you do that, you see that that's a sorted order. And that's really nothing deep. It's just the search tree property, but you see it in action here. So that's the way to that will draw the binary search trees. I think it's very helpful to do it that way. Let's do an example of how you find a key in this. Let's again find our 69. Any search would start at the root because we actually don't have anything else from the binary search tree. The way we keep the tree in our hands is keeping a pointer to the root. So we're sitting here, and now we're comparing the key that we're looking for with the key in the root. 69 is smaller. So what we're doing looks very much like binary search, except that there's no explicit computing of the middle. We just take the root as some approximate middle. Right, so it's smaller. That means we go in the left subtree. And everything in the right subtree is, by the search property, bigger than 69 and can be excluded from further consideration. And we continue like this. 12 is too small. So in this case, we go to the right. 57, again, too small. So we go to the right. And in this case, we have found a node with that key. So if we do a lookup, a get in the simple table API, we would get the key, we would get the value that's associated with this. So we get the value field from that object that's representing the node. Let's do another example where we don't find the key. So if we look for 83, let's do it a little faster. We start at the root. It's bigger than 77, so we go right. It's smaller than 85, so we go left, but bigger than 80, so we go right, and bigger than 82, so we would go right. But here's a null pointer, so we know the tree stops there in a way. And that's the indication, we found 83. If it was in this list, it would have gone between these two keys, but it's not there, so it is not there, right? So it would return not found or some exception. Okay? That's the easy part. If we have a binary search tree given, then we can use it to find or look up keys. Now I promised that this is a dynamic data structure, so let's make it dynamic. The first kind of updates that we want to look at are inserts. If this is dynamic, we should be able to insert new things. So let's take, I should take a different color. I reserved that dark blue for corrections after this lecture. So I usually avoid using that color so that I have one free to do corrections in the lecture notes before I upload them in case I sometimes do something wrong. Let's do green. How do you insert into a binary search tree? The first step is we try to find whether the thing is already contained. So again, start at the root. We do the same procedure as before. And you can follow along. It would have gone here, but it's not there. That's good. We want to insert it. So if it had already been there, we would have to reject that. But it's not there, so we can make room for it. And the way to do it is in the program, you would just take this null pointer and insert a new node with key 88 there. In the drawing, I'll first have to make room, but all I did was move this over. I hope you can see if I go back a few times. I've just moved this around. And remember, the picture is just imaginary. What this really is objects in memory with pointers to each other. So there's no moving around to make space. They stay where they are. We just add a new object. There's the new object. And we put it in the right place, but again, in memory, it would be anywhere. And now we connect it with pointers to the previous one, and that way it becomes linked into the tree. That's insert. And insert always works like this. You follow a path down, and if the element is not already there, you have to stop in some null pointer in some of these little squares. And then you can add your new thing into that little null pointer. We also want to delete keys again. If it's properly dynamic, that should be possible. Now, there's a few cases. Depending on what kind of node we delete, this is either easy or needs a little extra step. But let's go through it. If we delete number 11, key 11, of course, as always, we start by the search. And we find 11. Now, the important bit is this is a leaf in this case. A leaf is, I should have maybe introduced a little bit of tree and graph notation at this point. A leaf is a node without children. And we say parent and child and son or child. I try to use child as the neutral form. And then we have parent. Leaf is the one without children. What else do we need? Sometimes I say unary node for a node that has just a single child. Not sure how relevant this will be in this section. That should be probably all. So there's unary. If we have a leaf, the way to remove it is by just setting the parent pointer to null. So imagine this is no longer there, and you just replace that pointer with null, and gone it is. That's easy because there's nothing below it that would be disconnected from the tree. If we look at the second case, if we delete 69, let's do our search again. We found 69, so now let's get rid of it. But it has some children, so we can't just set the parent pointer to null. That would be wrong. But it has one null pointer. So what we can do is rewire the parent pointer to point to the single child of that node instead. So we get rid of the 69 and reconnect this. And then again, everything that was in the tree below this is still reachable. That leaves us with the last case, which is the only a bit more tricky one. So if we find a node that has the key we want to delete, but it's not a unary node and not a leaf, so it has two children. We'd like to do the similar trick. So we'd like to get rid of this node, but then we have two dangling children. Ah, shoot, what do we do with both? We can't link them both to the parent. So instead, we find the predecessor in sorted order. Remember, this is actually corresponding to this position in the sorted list. So it has a predecessor. Note it has to have one. If it has a left child, there must be at least one further node smaller than this. So it can never run empty. How do we find that? Oh, I circled the wrong node, you're right. Yeah, no, it's just a typo. Yeah. But it's otherwise correct. It's the right order, just incorrectly copied. So that's our predecessor, 82. Thanks for checking. How do we find this in the tree? We go one step to the left from 85, and then keep going right until we can no longer go right. In this case, it's a single step, but you can imagine in general, it might be, here's our node, then we can go here, 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 here. But at some point, it has to stop because we're running into that node in sorted order. There must be a last node, and then this one is our predecessor. Right, so we find this predecessor, and then we swap those two nodes or their values and delete instead this predecessor that we found. And the way the predecessor is defined, it means it definitely has a null pointer as the right child. So this doesn't recurse further. after we've done the single swap, we're definitely in the medium case, or maybe even the easy case possible. And so we can, the rest is done in constant time with changing 1 or 2 pointers. Question? He could have a left child, yeah. So 82 could have a, let's hypothetically, there's some other node and so on. That's all right. So we would then be in the medium case instead of the easy case. So when we delete this node, we would rewire its parent link to the single child. Yep. If you code this, you will actually not need to distinguish the easy and medium case. You're just rewiring a pointer, and it doesn't actually matter if that pointer is null or not. But I think it's a bit clearer to split it into 3 cases. Okay, that's all. That's binary search trees. So you can search, you can insert, and you can delete. That's pretty much all you need. You can build a symbol table based on that. I'll leave the details for the videos that I showed you or your memory from some undergraduate class. I want to briefly talk about how quick this is, though. That's an important part. Let's first analyze search. And for that, remember, so we have some binary tree. Let me add a small example without wasting too much of our time. When we search for, say, this node, the time this takes is to start at the root and follow the path down to this node in the tree. So the time for search is, if we want to be precise, say the number of comparisons we do of keys. That's exactly the depth of this node plus 1. Because at every node on the path from the root down to this node, we would have to do 1 comparison to check which way to go or whether we've already landed on the right thing. And here I'm essentially assuming that comparisons tell me 1 of 3 possible outcomes. Either one key is strictly smaller or bigger than the other, or they're the same. So it would be cost 4 in this case, and the node is, I guess we set at depth 3 because that's the number of edges, so depth plus 1. So the number of comparisons we need is the depth of the node. Let's say that we call this x plus 1. Now, in general, it's hard to say how deep a certain node is, but we can upper bound this by the height of the tree. By calling the entire thing t. And keep the plus 1. So if we know the height of the tree, then we know an upper bound for all the search costs. So if we want to be a bit briefer, let's call this h and understand that h is this, the height. And that's counting the number of comparisons. The rest of the work that we have to do is proportional to that. So you have to follow a few pointers, you have to access memory and so on. But in the big O terms, in asymptotic notation, big O of h is a precise statement for the total cost of the search. Now, if you look at what insert and delete do, they're also, so insert specifically is first a search, and then we create a new node and link it into the tree. So we already argued that this is at most the height. And the second part is constant time, with our assumption that the memory management is able to do that. But changing the pointers takes constant time on a RAM. machine. Now for delete, there were the 3 cases, but in a way it's still bounded by the height. So you had one search, potentially the predecessor, and moving a few pointers. The last part, again, constant time. And the first and the second together are at most the height. Because remember how this worked? We were walking down the tree to some point. We wanted to delete that node. Either it's already fine because it's a leaf or a unary node, or we had to find its predecessor. But then the search would start at this node and go further down. So it can't in total be more than the height. Of course, we could have been lazy and said, search is at most order h, big O of h. Predecessor is also at most the total height. So it would be 2 times the height, which in big O notation doesn't show up. The factor 2 is just swallowed. But if you want to count the number of comparisons precisely, you could do, and it's bounded by the total height. OK. So in summary, this is also order h, right? Big O of h. So all the 3 operations are bounded by the height of the tree. So it looks like the height of the binary search tree is a really important parameter. To summarize for what we've seen so far, this also translates to the symbol table operations. As I said, coding this up is a little extra step that we won't do here. But that's what you get from this. Now, how high is a binary search tree? Unfortunately, the height can be very bad. If you insert keys and what happens is this, or even if it's a little less, it could also look like this. Depending on the insertion order of your keys, you could get a tree that's basically one long chain. And if you have that, the height is essentially linear, n minus 1. That's really terrible. That means all the operations are just as slow as what we've had before without all the fancy trees and so on. Oof, bummer. So what do we do? The good thing is that this is a very rare and somewhat degenerate case. And you almost never observe this if you have some randomness in your insertion order. So more specifically, if you assume that the insertions come in completely random order, so you insert the elements according to some random permutation, then you can show the expected height is logarithmic. And I don't want to go into the detail of the analysis here. This is a lovely topic, but maybe I'll spare you with it for now. You can make this statement much stronger. So instead of just the expected value of the height, you can get something that quantifies how unlikely it is to be above a certain height. So you can make a statement as spelled out here in formal with formal quantifiers. Basically, whatever multiplicative factor you give me that you want above log n, I can tell you an exponent how unlikely that is. So in a way, it's a way to say not just the typical height is very close to this log n, also almost always it is if you have a large number of keys and they come in random order. Also remember, we discussed this in a bit more detail in the chapter on heaps. Any binary tree with n nodes must have at least this log, base 2. Let me stress that here. So in this sense, what we find here as the typical height of a random binary search tree when you insert things randomly is very close to the best possible height. So it's not just okay, it's almost as good as if you perfectly balance everything out.